Good morning, everyone, and welcome to the Jamaica Institution of Engineers Development Forum. I am Jane Walters. Myself and Javid Smith will serve as your moderators for today's session. So firstly, the JIE Development Forum is a platform dedicated to fostering insightful discussions, knowledge sharing, and collaboration among engineering professionals, industry leaders, and academics. Today, we are excited to explore key developments in optimizing industry, advanced control, and automation, gaining valuable perspectives from our distinguished speakers. We are privileged to have three esteemed speakers joining us: Dr. Garfield Denton, Dr. Alnoor Allidina, and Kevin Perrigo. Before we begin, here are a few housekeeping notes. You can use the chat for any questions that you may have for our presenters. This session will be recorded, and we will also have giveaways courtesy of NCB Capital Markets, so stay tuned. With that, let's get started. It is my pleasure to welcome Dr. Garfield Denton. We're honored to have him as our guest speaker. Dr. Denton is a professional chemical engineer and advanced process control engineer with over 20 years of experience in minerals processing and oil refining. He has been instrumental in the development of advanced process control applications at refineries in Jamaica and Canada. And today he will be sharing his expertise on the role that APC or advanced process control applications can play in optimizing industries in Jamaica. Over to you, Dr. Denton.
Thank you very much for that warm welcome. Sometimes when I hear a person speak about me, I'm still amazed. Okay, so let me just share my screen. I sent a request to share.
You have not been granted.
Okay. Okay. Please let me know if you're able to see what I'm sharing.
I am seeing.
All right, thank you very much.
Yes.
All right, so good morning, everyone. And I'm really grateful for the opportunity to speak about the potential improvements we could see in our industries in Jamaica if we further optimize our operations utilizing advanced process control or the layers of control above APCs, right? So the first thing I'll do is I'll just do a quick review of the various levels of process control. It is important to understand that each subsequent level of process control is built on the layer below. So the lowest level is our basic regulatory controllers. The next level is what we call our advanced regulatory controllers. Then we have APCs, and now we're moving towards constraint economic optimization. And then there's even another level above that, which will involve the use of AI and machine learning. It should be noted that as we move up the levels, we're seeing an increasing complexity, and the cost and benefits, however, don't necessarily scale with going up each level, but the overall improvements that we see both in safety, stability, financial results due to going up into the levels definitely improves. And I will spend a few minutes just explaining what each level of process control gives us and what potential benefits we could get as we move up in the layers. So again, the very basic level is what our basic controllers. We term these type of controllers single inputs, single outputs. An example here is like if you just have a control valve in a line, and you have a flow transmitter that is recording the flow, and you just manipulate that control valve to try and reach a particular set point for your flow. Well, if you compare this to what we used to do in the old days, because I did work at Windalco before its name was changed as a summer intern. and I worked in the precipitation area, and I used to go out with the guys that worked in the field, and they all had to carry sledgehammers. So if they wanted a change, you had to be big and strong to go outside and swing a sledgehammer to get any changes that you want, right? But as we've introduced more and more basic regulatory control loops, and we've built distributed control systems, DCS systems, so that we can have basic control over the most important parameters, then the need for us going outside with big sledgehammers has decreased over time, right? So the next layer, and even though we've moved above basic regulatory controllers, it is absolutely vital that these controllers are working well, because every subsequent layer above is entirely dependent on how well our basic regulatory controllers work. The next layer is what we call our advanced regulatory controllers. These are now like you have multiple inputs, but you still only manipulate one output device. I did a little drawing here trying to give an example where I have this tank where it's filled with like a liquid. I would like to control like the temperature inside the tank, but the heating medium is steam, and all I'm doing is measuring the temperature, and based on what the set point for the temperature that I want, I'm sending that signal to a flow controller, which would then regulate the volume of steam that we inject, that we pass through the line going into the tank to heat up the tank. There are many, many different types of advanced regulatory controllers. We have ratio controllers. I think these are utilized quite a bit wherever we have mixing of chemicals, or in the food industries, or where we're making paint, or whatever the case might be, where you want to mix a number of ingredients. So these advanced regulatory controllers gave us improved stability over our basic controllers. They've given us, improved performance. And companies that have moved up from just the basic regulatory controllers have seen improvements in their bottom line because of these controllers. Again, if the base level controllers aren't working well, then these ARC applications won't work properly. The next layer, which we will spend a lot more of our time speaking about, are what we call our advanced process controllers. They go by various different names. Some persons call them model-based process controllers. And the companies that make applications that do this type of process control, they go by various names. So say, for example, the ones that I'm most familiar with include Delta V, DMC, RMPC, which is produced by Honeywell. So depending on what box you go for your APC, it might come with a different name, but overall they all do the same thing. So instead of now relying on just feedback control to say, hey, I wanted like a set point of 50 degrees Celsius and my current PV is 45, therefore I have an error of 5 degrees, make a change in my manipulated valve or whatever output device to get my process variable closer to my set point. With APCs, I'm now using a model-based approach. So rather than depending on waiting for that error to arrive, I'm now able to predict what could happen sometime in the future and take action proactively to try and eliminate those errors, right? And this type of control now gives us the ability to have numerous inputs and numerous outputs. And we, as the persons who build and maintain APCs, are then able to implement the optimization objectives that the company may have. As an example, you might have like for a distillation column, you might have a particular cut point for your top end from your distillation column. You might want that value not to exceed 300 degrees, for example. We are now able to predict using all the independent variables that impact this IBP or whatever cut point we're looking at. And we're able to adjust those levers in between when we have the laboratory results coming. APCs also open up the doors for the use of analyzers, online analyzers, and soft sensors, right? So there are various other tools that come into play because we are able to implement advanced process controllers, right? Now, the
Dr.
benefits.
Denton,
Yeah, yes, go ahead,
I
please.
don't mean to cut you just a second. So
Yes.
there, I think the participant portion of the Zoom meeting is blocking a little bit of your presentation. So if you can minimize that for me, please, that would be,
Oh, I'm sorry. Okay.
I got it. Or if you can move it a little bit.
Is that better?
I'm not, yes, that is perfect. Thank you so
Okay.
much.
I apologize for it blocking the presentation, right?
That is fine. Thank you.
All right, no problem. All right, so the primary improvements that a company can see if we start to implement more advanced process controls, we can see significant improvements in our plant performance, profitability, because now instead of just running to a set point, we can now try to optimize the process and push it to the true constraints of the units, right? Across the world, the different companies have seen various levels of savings and bottom line improvements. I have here, sometimes they see between 300 up to like 2 million US dollars annually that an APC application has delivered to the company, right? I won't be spending a lot of time talking about constrained or real-time economic optimization because there aren't very many use cases internationally where we're actually utilizing constrained real-time optimization. In fact, where I work at the moment, we have a test plant where we're trying to implement one of these type of APCs. So the information and knowledge about these APCs or these type of systems is quite limited, but a lot of companies are investing heavily in trying to include not just the plant limits, but other constraints such as customer demand or inventory systems or blending systems. So more and more of the other external things that we need to consider when we're running a plant are now we are now able to factor those in how we run our units. So instead of just always trying to run to the operating limits of the unit, then if there's an external factor that has an impact, then we can consider that and adjust the unit's performance accordingly. This one is the one that I'm most afraid of. If you're older, like I am, and you've watched the Terminator movies, and you've seen how the world is moving towards the use of AIs, the more we develop these systems, the more I fear we're moving towards that type of situation. But maybe I'm just being paranoid, right? But the use of machine learning and AIs, that's a big field. We have a lot of companies investing into AIs. It should also be noted that we don't want to build these systems to replace persons. However, but if you look at how a person can respond to an issue versus how an application you can get vast improvements in response times and stuff like that. But at the same time, we still need that human interaction to be able to maximize the benefits from these applications. So even though we're moving towards here, I'm very cautious, and I would advise everyone to be cautious as well, right? All right, so I have here a graph that shows the potential improvements that each layer of process control can deliver to a refinery. And this graph is very telling. Say, for example, I'm going to use a rough made-up example here. Say, for example, the normal operating limit for like your fuel gas flow rate to your furnace is 20 gallons per minute, right? And that is represented by this red line here, right? No, when we had the traditional basic level controllers, we had large variabilities in our PV, which is represented by this green line. So on average, our fuel gas flow rate might have been 18 gallons per minute, but the variability might have been plus or minus 5 gallons per minute. So in terms of our throughput, we might have been only limited to 1,000 tons of material through our kiln or whatever material we're processing, right? So because we're limited to whatever average we can maintain without violating our operating limit, we've basically restricted our production rates to about 1,000. Then we implemented advanced regulatory controllers. And because of the improvements in unit operations and the reduction in variability, we've now shifted the mean from like probably 18 up to 19 gallons per minute. That has automatically increased the throughput that we're able to push through that furnace, largely because now we're able to push more fuel gas into our furnace. We're now able to, instead of just push through 1,000, we're now able to push through 1,200. Then we go to APCs, which further reduces that variability. So now we're averaging 19.5, and our variability is less than 1 gallon per minute. We're even able to push through even more material through that furnace. So what we've been able to achieve is a reduction in variability and at the same time an increase in throughput through the unit without the further increase in capital costs or investments, right? So this is one of the biggest areas that I believe most industries in Jamaica can increase their productivity, is if we are able to shift our means up to the true operating limits of our units by reducing the variability, by improving the way that we control the key parameters, then we're able to see an increase in production without an increase in the capital cost investment. Of course, we would still need to invest into the technology to be able to achieve this type of performance, right? The next layers now gives us the ability to run based on other constraints, not necessarily just those related to the operational limit. And because you're running to not just the operational limit, and you're able to do real-time optimization, then your true operational limit might even increase or decrease over time. And you're able to account for those. Again, the most important layer in all of this that I'm showing here still lies with our basic controllers. So controller tuning, having good working instruments, having the personnel to actually work on the basic level of controls, that is vital. I can't stress this enough. The success of every subsequent layer is dependent on the very first layer, right? So I took the opportunity to canvass several companies in Jamaica in preparing for this presentation. And what I found out is that there's only one manufacturing company in Jamaica that has an APC applications running. I might be incorrect, and if I'm incorrect, I'm open to be corrected in regards to that. But there's a big opportunity for all the companies in Jamaica if we decide to move from just utilizing the basic and the advanced regulatory controllers and move up to the utilization of more APC controllers, right? So what I've done, I went through a couple of the main production and industries within Jamaica, and I've looked at potential APCs that these companies could look at implementing to improve their overall production and their bottom line. So starting with the mining industry, there are APCs implemented internationally that look at like their grinding and milling speeds, how they're controlling their conveyor loads. Utilizing APCs like these can give us a reduction in our energy consumption. We're able to maximize our throughput and also reduce our operating expenditures, right? In terms of cement production, we can improve, again, the same example that I gave you, whereby we've optimized our fuel gas consumption. It can help us to increase our production quality, production throughput, sorry, the quality of the material we're producing, as well as you can also get greenhouse gas reduction from these improvements. Because say, for example, if you're only limited to making 1,000 tons, but because of how unstable your operations were, you were utilizing 20 gallons per minute of fuel gas, for example. No, you would then be able to produce 1,000 tons using 15 gallons per minute, say, for example, because now you're far more stable. You're able to push the unit a lot more, get more throughput through while using less fuel. So therefore, the quantity of CO2 and other greenhouse gases that we're producing would be minimized. I also have some suggestions here for the pulp and paper industry. Um, we could also look at improving our controls around our digesters, the bleaching units, and we could see an increase in the yield and a reduction in our consumables. Other industries, this one is quite close to me because I did spend a number of years working at Petrojam, oil refining, right? If we're able to, like, say, for example, optimize our distillation units, and or furnace operations, we'd be able to push through far more barrels of oil each day. We'll be able to meet our product quality specifications more consistently. And even the hydrotreatment operations, there are a lot of APCs now built around the reactor controllers, right? So those are some of the areas that we could see vast improvement in operations there. Also, because we're moving now towards real-time optimization, there are also applications being built that integrate our logistics into the whole operation. So our storage and blending of different products can be further improved through the use of APCs. Minerals processing, I spent a vast majority of my professional life working at both Windalco and Jamalco. And I know that we have APCs implemented, of course, but if we're able to really get these applications working well, we can see further reduction in variability. We can see an increase in our throughput. And through the use of soft sensors, more soft sensors than we currently utilize, we're able to have even better control over our product quality. In agriculture, there are APCs built around precise irrigation, especially now that I've read a lot about the drought conditions in Jamaica, where it is vastly important for us to optimize our water usage. So APCs can also help us there, whereby if we know that coming up into the summer months, we'll be limited by the volume of water that is available to us to irrigate, we can try to optimize what plots of land we irrigate and by how much. There are also APCs being used around internationally relating to like the application of fertilizers, as well as they also have APCs now looking at livestock health and feeding. In terms of power generation, which is a big one, the example I gave with the use of fuel gas, that's something that is applicable to all our power generation facilities. We can look at optimizing those boilers. We can optimize our steam pressure, steam production. All of this could give increased throughput, better control of increases and reduction in power generation based on demand. And yeah, there's so much improvements that could be attained if we were to move towards the use of APCs within our power generation facilities. And last but not least, in food processing, APCs could give us improved product quality, more consistency, reduction in waste, and energy consumption. Now, I've said a lot about the virtues of APCs, but there's another reality that we have to face. This technology is not free, and in some instances, it can be quite costly. However, the cost of implementing APCs is highly dependent on a number of various factors, and I have a couple of them listed here. if we decide to have like a custom APC whereby we're building this application specific to our particular process. I see Karine has her hand raised. Should I take that question or wait until the end?
Wait until the end, Dr. Denton.
Okay, right. So if we decide to go the custom route versus the out-of-box solutions, then that could result in an increase in cost. The size and scope of the application also adds some cost to the application. Software and licenses. If we decide to do consulting, like say, for example, if you decide to bring in Honeywell or one of these external companies to build the APC for you, or if you have the resources in-house to do it yourself, that can also reduce the cost of the application. One of the most critical, and I can't stress this one enough because I benefited greatly from this, is the training of operating personnel as well as engineers on APCs. This is a cost that is unavoidable, in my opinion, because in order for us to keep the APCs online and for the application to always be delivering at its optimum, we need the persons that will interface with the application to be fully aware and fully trained on how to utilize the APC. Then the next cost is related to maintenance costs because it's not just a one-time cost in just acquiring an APC, training your personnel, but the ongoing costs for whatever new instruments that you had to install for your APCs, all of that will also impact the total cost for the APCs. What I have here is the international experience in terms of the return on investment for the various industries for a new APC application. Say, for example, in the oil and gas industry, the APC pays for itself within 1 to 2 months. So say, for example, if you spend $1 million, for example, for a new application for your distillation column, then within a couple of months, the savings that you've gotten through improved product quality, increased throughput, all of that should pay back for itself. In refining chemicals and petrochemicals, that's between 3 to 6 months. For industrial power, within a year, the APC would be able to pay for itself. The final thing I will talk about is also one of the most important aspects of APCs. What is required to actually implement an APC? So the very first step is that we'll need to justify the APC. So how do we justify an APC? We do what we call a benefit assessment. And what we typically do when we're doing these benefit assessments, we look at a particular variable which is of interest. Maybe it is the overhead temperature of a distillation column. We look at what the mean is and its current variability. Then we look at what improvements in our operations can be attained by reducing the variability in this operating parameter, right? So when we're building brand new APCs, we typically look at what a 50% reduction in the variability could yield, right? So we reduce the variability by 50%. We're able to shift the mean either up or down, depending on where we want the mean to go. And that then would result in probably an increase in production or an increase in yield. And then that can be translated into a dollar figure. So then when we complete our benefit assessment, we're able to come back and say, hey, within 15 months, within 10 months, within 3 months, if we implement this APC, which gives us this improvement in this operating parameter, this is the benefit it will deliver to the company on an ongoing basis. So each month we will be achieving this amount of benefits because of the implementation of the APC. And if that value now is passes, the rigorous checks that we will have to do whether or not it is something we can afford as a company, then it is a good APC solution to pursue. So the next step is what we normally term or operating philosophy. So this is the opportunity that the company would get to get everyone that will be impacted by the APC to contribute to the overall process. So because not only the management that will decide whether or not we're going to pursue the APC, but we also need the feedback of the field personnel. So we'll come together and we'll come up with what the overall objectives for the particular process is. Maybe the overall objectives are we want to see improved safety, we want to see a reduction in greenhouse gas emissions. Whatever those objectives are, everyone in the company gets their opportunity to give some feedback to what the operating philosophy for the company or for that process should be. And as a result, that operating philosophy then becomes the basis on which we optimize when we implement an APC. Also, we also have to understand our operating constraints and what opportunities are available to us if we're able to implement an APC. The next step is that we'll have to prepare. So this will involve like an instrument audit. We'll have to look at our base level controllers because the APC is 100% dependent on the accuracy of the instruments that we have, as well as how well these base level controllers are working. So we'll have to do a lot of controller tuning. Also, in this phase, we'll have to also start considering what training requirements we will have for our engineers and our operating personnel. One of the vital areas that from my past experience that I think we can do a significantly better job of in Jamaica is around our documentation systems, right? So our management of change. So if we make a change to a process unit, maybe we have a pump that isn't working properly and the pump was a 200 horsepower pump, but we only have a 150 horsepower motor in the shop, and we replace that motor with the lower rated or a higher rated one. We have to be able to properly document that, because if in the future we want to do something and we assume that based on how the plant was designed, the pump is still using 200 horsepower, and we install valves and other pieces of equipment that is assuming these kind of all of this is still as was designed, it will yield a lot of issues in operations further down the line. One of the other weaknesses I think we have in Jamaica is around our P&ID management systems. So if we mark up or make any red lines to any of our P&IDs because we've modified the process, we have to do a better job of improving how we document our P&IDs. The next step is we would have to do the building of the model. So we'll go and do a pre-step test, a step test, and then we'll come up with these models that give us the information that we need to build the APC. We will then design the APC, then we'll commission, and then for the continual success of the APC, we'll have to ensure that we properly train all our engineers, all our operating personnel, and we'll have to come up with a system of evaluating the performance of the APC on some basis. So most of the places I've worked in the past, we've tried to get a marker of how well the APC is performing each month, right? And then we'll also need to look at our PM schedules for our instruments or equipment. And all of that is what will be required for us to implement an APC. Basically, that's all I had for you guys today. So over back to you, Jan.
Thank you so much, Garfield, for that insightful presentation. And I just want to take the time to welcome all of the new persons joining us. Welcome again to the GIE Development Forum. Today we're focusing on optimizing industry, advanced control, and automation. We just heard from Dr. Denton. We have Kevin Perrigo coming up at 11:15 a.m. and Dr. Alnoor Allidina at 12:30. Just a reminder of a few housekeeping notes. Use the chat for any questions. Session will be recorded or is being recorded, and we will have giveaways courtesy of NCB Capital Market. Any questions for Dr. Denton? Any questions? Any questions for Dr. Denton? You can just post them in the chat.
I believe Karine Turner had a question. I believe she had raised her hand earlier.
Okay. All right. I'm not seeing any questions or any hands being raised at this point. I will give it a few more seconds or a minute or so, and then we will get into the giveaway.
There's a question from Dave Muir in the Q&A. He is asking, is the economic system pulling data from the company ERP?
Can you expound on ERP? I'm not familiar with that term. I'm really sorry.
Oh, um, I think the term stands for enterprise resource planning. I'm not sure if it's the
Yes,
same
yes, it's
reference.
Okay.
enterprise.
Okay.
Yes, it's enterprise resource planning. Sorry, I
Okay.
didn't know I was allowed to speak. I was trying to type as fast as I could.
Okay. So you were asking, can you repeat your question again now so I can better answer it?
Yeah, sure. The system that you mentioned, the one that does the optimization, the economic one that you mentioned, I was just wondering if, in terms of it being able to factor the variables that you mentioned, if like it's actually talking to the company's ERP system. Oh, you're muted.
I'm saying that area is something that is still being developed, but the plan is yes, to speak with all the relevant external software that can give us information to guide the operations. That is the plan going forward. And whatever information I currently have, it's not something I can share because it's still an era of development for many companies. But yes, the yes is the answer to your question.
Okay, thank you.
Okay, thank you. Any other questions? Okay, moving into our giveaway.
There's
So we
actually a
have,
question in the chat.
okay,
Sorry.
no problem.
Karine Turner is asking any suggestions as to how we can optimize the updating of our PNID.
All right. Well, the system that is used that I am currently using is a proprietary system, but I believe on the market there are a number of different companies that offer document management systems. I'm certain we even because of our relationship with Honeywell, we might be able to find a system that is Honeywell based or Honeywell has been integrated with. But in the system with the system that I'm currently using, it is a stamped out, stamped in type system where if a change in a PNID is to be made, you would have to check out the PNID. You make the modifications. It is then signed and stamped by a professional engineer certifying that the change is acceptable. If it is going to be used by someone to, like, say, for example, modify some pipelines or something, the company that the engineering company that will do the work, they will also stamp the PNID to certify that it is the as-built PNID, and then we would sign in back into the system that new updated PNID. So it would be appropriately stamped, appropriately time stamped as well, indicating that it is the latest version of the PNID. So any future work or any future modifications to that PNID would have to be done on the latest version of that PNID, and we don't end up utilizing an outdated drawing, which might not have the true as-built modifications out into the process. So there are a number of systems like that available on the market, but we'll have to do some research in determining what is the best application for our particular use based on how we actually do our work right now. So I know Karin is at Jamaica, so yeah, yes, we would have to try and properly understand how and who would be making the modifications to the PNIDs, and then choose the appropriate system to manage that for us.
Thank you, Dr. Denton. So that question was actually from Gary Thompson.
Okay,
Right.
yes.
So we have a little bit of a mix up with the names coming in. So I would like for each participant or attendee, if you can just type your name in the chat so that we have it right when we're issuing the certifications for this webinar. Thank you.
We have two more questions for you, Dr. Denton.
So Richard Artwell asked, are there any examples relating to a hatchery or poultry?
In my preparation for this presentation, unfortunately, I did not look into poultry farming. But just based on what my research had shown, potentially there might be an APC, because I did see one related to livestock health and feeding. So maybe those type of APCs could help with poultry farming. But again, I did not look into details beyond just what is available out in the wider industry, internationally. Yeah.
I believe there's another question. Engineer Dave is asking, any thoughts on machine learning control and its data requirements? This may be a limitation.
Okay. So I did make that joke. I always think that it's funny to myself because of my fear of that, what I saw in those Terminator movies. But yes, I can only think of one facility in the world that has moved up to utilizing machine learning. At least that was the only one we were privy to some information about. Most companies that have a DCS system, they would have an inbuilt data storage system, whether it is Pi, PhD, whatever the data source is. Typically, you would probably just link your system to that data historian, so you can have historical data, plus the current data would be feeding into your machine learning. And as a result, you could get real-time improvements to your models that you have. And as the AI learns about your process, it could suggest improvements or changes to the models. And I prefer that kind of solution where an AI makes a suggestion rather than makes a change, right? So you would still require the human interaction and human input into making the changes, right? So we don't want to give full control to the AIs. So I would prefer if we were to go towards that kind of system, we would still have the verification being done by someone rather than the computer making the changes all on its own.
Thank you, Dr. Denton. Any additional questions? There's a question from Dave Muir. I'm not sure if you answered that already. I saw one. It was asking if you worked with Gobin, Dr. Denton.
Yes. So in terms of, well, all of us who have worked as APC engineers in Jamaica, and again, I'm assuming there's only one site in Jamaica that currently has APCs. He was instrumental in training a number of us and giving us the opportunity to learn this field. His approach was we're all controls engineers first, and then you're a specialist afterwards, right? So yes, I did work with Gobin for many years, and again, I give credit to Gobin for the opportunities that was given to a number of us as APC engineers.
Thank you so much, Dr. Denton. And likewise, I give credit to Gobin as well and yourself, Dr. Denton, for laying the foundation for APC engineers in Jamaica. Thank you very much for your presentation. If there are no further questions, I'll move into the giveaway questions. So the first question is in relation to the benefits of APC controllers. So throughout Dr. Denton's presentation, he would have mentioned the benefits and how they would help to optimize. APC controllers can optimize industries in Jamaica. So the question as I'm posing to you, if you can list 2 benefits of APC controllers, and you are to send the answer to the JIE WhatsApp number. The WhatsApp number was posted in the chat, but I'm just going to give you a quick reminder. The number is 876-772-1666. So that is 876-772-1666.
Okay. So we'll just move to Dr. Allidina. Dr. Allidina, are you ready? Are you here?
Hello, yes, I am here.
Okay. So Dr. Alnoor Allidina is a professional engineer and holds a PhD in systems engineering from the University of Manchester Institute of Science and Technology. He is currently the president and CEO of Engineering and Technology Associates, Inc., located in Toronto, Canada. His company focuses on the improvement of business operations for its international clients with the implementation of innovative wastewater treatment technologies, such as the largest water utility in Chile, as well as work done for the government of Jamaica, just to name a few. Today, his presentation will look a lot at the automation systems used in wastewater plants and how they help to optimize results, particularly through improved efficiency, increased performance, and reduced energy costs. We thank Dr. Allidina for joining us today and look forward to a very insightful presentation. Dr. Allidina.
Thank you very much for the kind introduction. A lot of the stuff that you mentioned, including my PhD and the graduation, I have to say it was a very long time ago, but I am still here, very excited about the work that I do in the field of automation and control systems. I would like to thank the previous speaker, Dr. Garfield, for taking us through some of the concepts of advanced control and so on. and hopefully I'll try and build on some of that. So with that, if I can proceed and share my presentation.
Go ahead again, Dr. Allidina.
Yes. Hopefully you can see my screen.
Yes, your screen is good, sir.
Great. Thank you very much for confirming that. So I'm going to spend the next few minutes taking you through some examples, shall we say, where we have and one can implement some higher concepts in controls and automation. One or two examples are fairly high-ended. One or two examples are quite simple. But the point I wish to make is that a lot is possible with a little bit of knowledge and interest and a little bit of cost. As I say, you need to have some imagination and knowledge to be able to achieve some good results. This doesn't matter if it's a very sophisticated system, as I'm going to show you, or something a lot simpler. So with that, I will take you through a presentation here, which is really going to be talking about how we use automation at various levels to improve efficiency, increase performance, and reduce energy costs. Just one or two things, as I was mentioned here, that, over the decades, we have grown up with the idea about being able to control devices and this, that. And Dr. Garfield showed us some simple and some complicated examples of control systems, which for decades now, industry and academia has been doing it. But now we are expected to not only do that, but to do it much more efficiently, trying to save money, trying to improve performance with the same tools and hardware and software that we have, but with some additional knowledge and focus. So what we need, as I say, is some imagination and knowledge so that we can achieve something very significant. If you are a fan of people like Einstein, he used to say that imagination is more important than knowledge. I kind of agree with that, but I add in our field that we need both. We need the imagination, and we also need the knowledge to be able to do something better. The first example I want to take you through is a system that was implemented in Canada, in the city of Toronto, what I call water system optimization. The box that you see in front of you, the yellow box rather, says Tool Transmission Operations Optimizer. It's a system of software and hardware that basically takes into account in real time all the information that you see on the left-hand side. By hydro rates in Canada, we mean power or energy rates, your power provider rates. SCADA data is real-time information coming off the water system, like reservoir, tank levels, various equipment status, and so on, with pumps and so on, and past demand data. It goes into a mega box, and that box produces an optimized output as to how to run your transmission system, water system, in order to save energy and save costs. So the software here consists of different blocks relate to predicting your demand water usage in various pressure districts within the city of Toronto. There might be about 10 or 12 pressure zones, each with a predicted demand, where we have models for doing that. We have detailed information about the cost of energy. We have a detailed hydraulic model, and the critical part about all this is this mathematical optimization, which takes into account the hydraulic model, the demands, and we have constraints. The earlier speaker talked about constraint optimization. This is very much needed here, whereby you optimize a system based on certain constraints. For example, in the water system, you may want to make sure that your reservoirs do not go below critical levels and so on. And of course, you have to make sure that then overfill system equipment status is taken into account, whereby you may have some large pumps that are out of service, are being commissioned, are being fixed, and so on. And then we have a mathematical cost function that include all the pumping costs and the production costs. We have lots of analytical algorithms, data integration, and then we have online monitoring systems. So all of that then goes into this diagram here, which shows you the system architecture. The things that I spoke about earlier, the key part is the hydraulic model here in the middle of this diagram, and the control strategy component, which is a ton of mathematics, nonlinear systems optimization, multivariable, of course, because we've got lots of inputs and outputs happening here, and all the constraints go in here, and this produces the result. It takes, on the computers that we are running currently, it takes about 15 to 20 minutes to run an optimization cycle. The city has selected right now to run this optimization system twice a day. So they run it in the morning and then again in the evening. It used to run about 3 times a day, but for operational reasons, they have now changed it to twice, which is quite adequate. This shows you some of the details of the model. On the left-hand side, you see the demand model that predicts short-term demand using a set of model parameters. The model parameters can be determined, can be calibrated. So basically, you have a set of equations, analytical equations, that predict based on the weather, the temperature, the rainfall events that have occurred in the last few days, the past demand. There's an equation that will tell us what the demand is going to be within that particular pressure district. We have models for weekdays, for weekends, for holidays, for about 12 or so pressure districts. So that churns away every time the optimizer runs. The demand model predicts what the demand is going to be for the next few days. Because one thing that this optimizer does is to run the model of the optimization over a 7-day cycle. In a water system of this sort, is not enough to optimize just instantly, but you have to take into account what's going to happen over the next few hours, even a few days, because some of the rates actually are related to a weekly billing cycle. We have a hydraulic model here that represents hydraulically the system in terms of reservoirs, levels, the control strategies going there. And then we have the mathematical part, the control strategy component part, which does the optimization based on the time varying constraints. System equipment status taken into account, very, very important. And the cost function includes the pumping costs and the production system. Here is the optimization itself, where we take into account the total cost, including the sum of all the pumping station costs to run it, and the production costs. In this case, the city has 4 sources of water. Each plant has a slightly different cost of production. So we can feed that into optimizer, and optimizer can decide to use less water of the more expensive plant and more water within the hydraulic constraints. So that's very useful. The control strategy then minimizes the total cost subject to the constraints. And the idea is to cut back on costs and the energy use as well. This is a graphical picture of an older variant of the graphical user interface. You can see here the water consumption, the reservoir storage, the energy consumption, total cost of energy being updated continuously on a real-time basis. And the operators then go and dig into deeper into the water demand by pressure district, the pumping schedules, the water storage. You could see profiling over the next 7 days to 30 days even, how the tanks and the reservoirs are going to be behaving over the next few days. You can look at the water quality, and of course, you can look at the energy costs, because this is the key parameter here. This shows an example of hundreds of results of this sort, where you see in the top figure here, the pumping station flow. Before the optimizer was used, this is typically, the red line was typically how the operators would run the system. There's no information that they would have in terms of how to change the pumping from this particular station, from this particular plant. But with the optimizer in there, based on the diagram figure below in the blue, which shows the cost of energy, we have a time varying cost in Toronto. You can see that the optimizer is reacting to that and pumping more when the energy is low, etc. And each and every station is about 40 pumping stations that behave in a similar way. The final result was lots of money saved, less energy used. The City of Toronto has got awards from various organizations in North America based on this system. This is a complex optimization control system in the world. It takes years to build. It takes a few months to implement, but the savings are tremendous. If one can achieve that, then that would be fantastic. Now, this is at the very top end of optimization, what I call. We can go in something simpler, still with the idea of using our imagination and some knowledge about how things work. This example shows here or discusses just one single wastewater pumping station. Typically, the station is controlled based on pumps being programmed to start and stop based on the wet well level. We've done this for decades. Everybody does this everywhere you go in the world. However, if you study closely some of the pumping stations, you think that's something else one could do by using our imagination and knowledge. Right? So what we've implemented is what I call a model predictive control, whereby the pumps not only start on the actual level as in the standard approach, but it takes into account a predicted level. What this algorithm does then, it says that I will only start the second duty pump only if the system determines that the first duty cannot cope with the situation, meaning that the wet well level will subside if you wait 10 minutes, 15 minutes, half an hour, and you can set all these parameters. In this way, you can prevent a second pump starting. Now, for large pumps and utilities that pay heavily on a standby charge, this can be a substantial saving in costs. Not only that, but you've stopped a pump, a mega pump starting for 20 minutes and switching off. That contributes to the wear and tear of this pump. So that's the idea. Here it shows pictorially that you're using some dynamic information about the wet well. Here's your MPC, the model predictive control. Quite simple as a matter of fact, because the dynamics involved in a wet well are absolutely very simple. You then program this in your PLC or controller, and you use that to start and stop pumps. This shows here a case, in a real-life case, where the inflows and outflows for this wet well pumping station are shown on the left, and the actual level is shown on the right. So the second pump did come on here for a short while and then went off. When we put the NPC on, the second pump didn't start because the algorithms determined that really without turning this pump on, the wet wells will be under proper control. This won't be an issue. However, if the algorithm finds that no, there's really a surge in incoming flow, the wet well is increasing, it will immediately start the second pump. There's no issues there. So the conclusion of this is that the simple algorithms with some imagination and knowledge, we can use it to lead to savings in operating and maintenance costs as additional pumps are prevented from being turned on. And as I said, for large pumping stations, the savings can be quite significant. A third example, this is the case in a system in Brazil, where they approached me to look at the control situation, actually quite simple, but they were not able to control the DO in these reactors here. There are 4 reactors with 4 DO controls. It's because from a process point of view, they kind of simplified the implementation by creating 1 header with 5 blowers into it. And then this header was then feeding the 4 tanks. And not only that, this header, not shown in this diagram, was also being used to feed air elsewhere. So there are all sorts of disturbances happening and so on. And they found the DO was all over the place. And the DO was quite important for them to control because without it, they couldn't get the proper mixing in the tanks. They required low ammonia concentrations, and the chemical engineers and the process engineers know how important the DO is. For us control engineers, our job is to control the DO. The solution is actually quite simple. In order to minimize the absolute noise on the measurement and so on, we typically use some kind of a filter. In this case, it was a very simple filter to eliminate the noisy measurements, so you have more stable control. You have to be careful when you do these sorts of things because it can lead to instability in some cases. Where we then designed the systems whereby it was a multiple loop system whereby the blowers were controlled on and off based on header pressure. And the pressure control was based on a PID algorithm. The first speaker, Dr. Garfield, did mention this sort of single input, single output control, where we have a set point, measured pressure, and that's controlling the set point for the blower. And then we had the control of the DO itself based on another PID loop, single input, single output, which was just driving the valve, each valve controlling the air controlling the air into the tank. I'll go back to this diagram again. We have a loop which control the header pressure, and the blower speed was controlled by maintaining the pressure in here, so that when other users took air out, we were able to quickly automatically change the blowers based on how many were online and not online to control the pressure here. Then we had a control loop around each valve and around DO. Assuming that the pressure was now relatively constant, we were able to achieve DO control by using this valve. Now, there's an extra step that one could put in if there was issue in these controls for the DO. By using what the first speaker spoke about was multi-input, multi-output, but I call it a cascade loop, whereby you would have the DO measurement and requirement loop driving a flow control loop and control the flow around this valve. But nonetheless, it was not necessary for this to save on costs for extra instrumentation, extra controllers. We designed a loop which was implemented straight from DO to the valve controls. I'd like to move on and talk about a plant in wastewater plant automation. This one is in Jamaica, actually. So many of you will know this. I believe this one is at Perth in Manchester, in Jamaica. Once again, the idea is about having proper and optimal plant operation. So whereby the plant is fully automated. There's not a single thing that the operator has to do, operations has to do for this plant to work optimally and fully. The plant has, based on MABRs, membrane aerated bioreactors, it has the usual equipment in there in terms of screening, the aeration tanks, the secondary clarifiers, UV disinfection, sludge management, and as I mentioned already, UV disinfection. This is the process for this plant in Jamaica. Quite typical, the only difference being that here in the middle, the anoxic tank has the membranes, which are very efficient in terms of the usage of process air. So this sorts of technology utilizes only, I would say, about 15%, maybe 20% of the air normally required in an activated sludge plant. So the MABR is a very efficient process. But this is not my topic here. My topic is automation. So we talk about that. Typically, you have any device. We have a hierarchy. I'm only showing 2 levels here. We have a local panel where we can control the device through either the electrical control panel, the MCC, or a local panel. Pictorially, we can put that mode of control into local so that the operations can only be done from this local panel, or we put it into remote where the control is transferred to a PLC-based control, which is all graphically based. There's a human-machine interface. And within this PLC, there are all kinds of modes, program manual auto modes. We program typically what we call mode permissives and operate permissives. Mode permissives are it's a logic that allows auto mode to be entered, for example, because certain conditions will not allow the operator to put the device into auto mode, or the logic to put the device into auto mode from a safety perspective. Also, there are operate permissives. Simply put, for example, you might include a low-level tank, a tank low level as an operate permissive, meaning that if the tank is at low level, the pump cannot turn on, the pump feeding out of the tank. So those sorts of protections are inbuilt into the logic. The plant and all the automation that we do for these sorts of projects, including a few in Jamaica, have a relatively low-cost graphical interfaces. You don't have to spend a lot of money in there, but functionally they are great. This is a touch screen, so you can actually go and touch the buttons or touch a pump here, and the pop-up would pop up to control the pump of this sort. For example, on the left-hand side here, this is a control thing that pops up on the screen to control the feed pump, the flow control, flow control valve. These in the middle here are to control the digested sludge pumps. All of these are standard templates, meaning every device is programmed the same way. So if an operator is trained on one device, is trained suddenly on 100 devices as to how to operate them. All the pumps have automatic duty mode selections, so you can toggle the duties automatically, or you can set them manually if you wish to, but typically they're just run on fully automatic mode. This is the same plan here, shows a fairly complex sequence, completely automated in terms of sludge and supernatant control. Now, point I want to make here is this, that more often than not, including even in other countries other than Jamaica, typically these sorts of controls are left to operators. So the operators have a direction saying at 3 p.m. you'll come and waste some sludge for 1 hour, and then you'll do this and do that. And every day they have to come and do this. And sometimes they are late, sometimes they're early, sometimes something is not happening correctly, and so on. But our philosophy is that, look, whatever the operators can do, we can automate this. It takes maybe a few days of thinking and programming and commissioning and setup, maybe about a week, shall we say. And then when it's done, it works like magic, meaning that 3 o'clock, something will happen because it was programmed to do so at 3 o'clock. It'll happen for 2 hours every day of the week. The same thing will happen without changes in the performance and so on. It may look complicated, but at the end of the day, it's really mimicking what an operator might have done, but more precisely and more correctly. So with a little bit of low cost operations and controls, you can fully automate the plant. And not only that, you can also include at a low cost some remote monitoring. So the authorities in charge, and I'm not sure at the moment, actually, I think Mr. Garth Jackson was around in the audience, whether NWC is already operating or planning to operate this, but remote monitoring is available for a plant of this sort, whether it's NWC or NHT. You could be sitting in your offices and monitor what the plant is doing. The next example I want to show you is a water system in St. Lucia. It's a small island, as you will know, of course, but its water system is distributed around the island. The terrain is not so easy in terms of hills and mountains and narrow roads and so on. And it's quite a challenge, and it's a lot of inefficiency in terms of time of operators, cars used to drive up and look at the tanks and turn pumps on and so on and so forth. So wisely and correctly so, the authority, WASCO, the water authority, decided that they should look into some kind of automation. So we are designing currently, we have designed it, they're in the middle of implementing this now, or they're rather going to start the implementation. Implement part of the SCADA system because of budget constraints that will automate the system. And here are the objectives that they've identified, and the system will deliver this. Okay? There'll be control and monitoring, supporting the operating process objectives, meaning that the tanks will be automated in terms of filling and emptying. The pumping stations will be automated, low-cost automation. All the alarms will be managed correctly and reported. There'll be data storage and reporting happening for regulatory purposes. It'll improve the overall efficiency of operations, of course. When I was there for a couple of weeks studying the system, I knew of operators having to drive every day, half an hour each way to look at tanks and pumping stations and so on. Once the system is in place, the same operators will be doing something else. They'll be monitoring it, sitting at their desk, rather than driving and using gas and whatnot. There'll be reduced power consumption because it'll be programmed to work in the way so that it operates optimally. Now, it'll optimize staffing levels, as I indicated. And eventually, once the data is gathered, they'll be able to fully support the hydraulic and water quality model. And I personally am very keen to see the hydraulic and water quality model runs in parallel with the SCADA system, pulling data from the SCADA system so that the model can then be improved, and that'll help improve their design of water systems as well. And last but not last is the system security, because part of the SCADA system will also monitor intrusions and things like that at the pumping stations and the tanks. Overall, there are areas of opportunity. I will not go through this in detail, but customer satisfaction, environmental responsibility, and overall operating efficiency. Each of these areas of opportunity has been drilled down, discussed with the authorities, with the operators, all stakeholders. Everybody made an input to this table, and we said this is how the SCADA system is going to target and improve each and every entry into this table. The development of the SCADA system, we broke it down by, first of all, looking at the requirements. What are the functional data requirements for each type of facility? What do you want to do at each water tank? What do you want to do at a pumping station? What do you want to do at the treatment plant? Then, rather than just diving straight into the specifications, we said, let's develop some standards for all your hardware and software, so that not only after this project is done, the standards will be available for the next 10 years for the authority to use as they keep upgrading the systems. We then had what we call a SCADA a project delivery process whereby we take into account how the SCADA systems will be operated and maintained and so on. We had to review the existing system that they have because they did have elements of SCADA system there, and a plan to improve and modify and upgrade it. And then this finally fed into the overall plan for the SCADA system. This picture shows at a very high level the SCADA system that will eventually go into St. Lucia. Only components of this will be implemented in phase 1 because of budget constraints, but the hope and the plan is that eventually over the next 3 to 5 years, they will implement the whole SCADA system. Finally, when it's implemented, the SCADA system will be able to then not only help operations, but also help maintenance and also help with data to other departments. That is the goal. And with that, I would like to finish my formal presentation and then hand it over to you. Thank you.
Thank you so much, Doc. All right, at this point, I'd like to see if there are any questions to be answered. Okay, so Dave Muir has asked if there are any examples of the quality models used along with a hydraulic model in the optimization diagram.
I'm seeing the question. Thank you for the question. The quality models, do we mean the water quality models? If that's the question, then yes, the hydraulic model has an embedded chlorine residual model.
Okay, Dave, you may unmute. Did that answer your question?
I'm going to type the answer here too.
Well, yes, I was just wondering if it's two models, it's the hydraulic model and the quality model combined in that block.
Yes, it's combined.
Okay.
However, we can turn on and turn off the water quality model. If the operator didn't want to be bogged down with water quality models, I don't see a reason why, because it does take a little bit of extra computation, but not a whole lot. It's an extremely useful thing for them to have because they do see that the occasionally, depending on the weather and the heat and all that, they will begin to see the chlorine residual, what they call quality, start to deteriorate in a certain area in the city, for example. If that happens, and we see that happening, then either manually or automatically, the optimizer can start invoking reservoir cycling routines. By this, I mean, I didn't go into the details of the optimizer and the algorithms, is that each reservoir has maximum and minimum limits set, not fixed limits, but profile limits. So what the algorithms can do then is to change this minimum and maximum limit so that they go up and down, up and down, up and down, and the optimizer starts, and then it tries to fill the reservoir and empty it, fill it and empty it, and they will do that, say, 3 times a week, which is something that they would do manually anyway before the optimizer kicked in. We studied as to what they did with the water quality issue. They simply would empty out the reservoir as much as possible, fill it up again, empty it out, fill it up again, empty out, and so on, 3 or 4 times. So now the optimizer algorithms mimic that basically, but in an optimized manner, so to speak, because all the algorithms are still working while those limits are now being respected. So that's very useful to have for them.
Okay, thanks, Doc. Are there any other questions at this point? If not, we'll move right along to Kevin Perrigo. Kevin, are you here? Thank you so
Yeah,
much,
sorry
Doctor.
about that. I was gonna turn my microphone on. Can y'all hear me okay?
Yes, but give me 1 second. So, Mr. Kevin Perrigo is the Senior Product Manager, Valves, Actuation, and Instrumentation for Epic Eastern Industrial Supplies, Inc., located in Jacksonville, Florida, USA, whose main products focus on valves, automation, instrumentation, and controls. The Epic Group is dedicated to supporting the Eastern sales force and its customers with the knowledge, experience, and products to solve any flow, isolation, and control needs. Kevin has over 18 years in experience in the industry with a focus on isolation and control valves for general to severe service applications. His presentation today will focus on the brands, types, and applications of various valves and instruments used in the industry for industrial flow control. For those who are very keen to learn about these applications, I am certain you will not be disappointed in the wealth of knowledge to be gained here today. So we apologize for the late start, but you may go ahead, sir.
Thank you very much. Well, I very much appreciate y'all having me today. I've actually spent a good bit of time working with customers in Jamaica, specifically in a lot of the bauxite mines, as well as Red Stripe and New Fortress Energy. Can y'all see my presentation okay?
Not yet.
See if I can get this shared.
Try again, Kevin.
Yep, I'm going to sit here a little share screen. Yeah.
Yes, we're good now, sir.
I'm seeing the presentation as well.
Excellent. Thank you very much. So my presentation, as you mentioned, would be basically surround the valve applications as well as valve actuation. And I'll just touch a little bit on some control or some communication protocols that can be used in plants and systems to communicate with those with the automated valves within those systems. So first I wanted to kind of touch on some of the different types of valves that there are within the industry. These are the most common valves noted here. The gate valve first, that's the gate and the globe valve. The first two are what we consider a linear multi-turn type valve. They're probably the oldest designs within the industry. Gate valves are typically used strictly for isolation, meaning they're just opening and closing to isolate flow from one section of the plant to another. Then the globe valve itself is typically used for throttling applications where you're trying to adjust flow and get a certain, let's say, gallons per minute of flow through that valve. Like I said, these are both linear valves to where it is a multi-turn operator. A 3 or 4 inch valve may take 15 or 20 turns of the handle to get it closed. And then we go to the right-hand side here, the quarter turn. As the description mentions, this is really just a part turn. So it's a 90-degree turn of the stem to go from open or closed. The different valves in those applications would be ball valves, which you'll see here. That is a full port valve, typically it could be used for isolation or throttling, depending on the application. We'll probably touch a little bit more on that later. Then there are butterfly valves, which have a disc within the line that's used to seal. And then a plug valve, which is similar to a ball valve, but just a different kind of shape geometry of the isolation plug. Kind of between those two, we've got what we call a non-return or check valve. That's that's a really a valve that's doesn't require external actuation. It is used to stop the reversal flow. You'll see as flow starts through the valve, the disc would open. And that's used to prevent backflow. As soon as backflow is sensed, this valve will close automatically to isolate anything that is upstream. They're typically used off of pumps to protect the pump because the impeller of that pump, if it gets backflow, can often be damaged. So that's kind of a safety feature within the system. Like I said, there's really no external actuation required of that. It uses flow reversal to close the disc, or technically there's a spring that would have closed the disc just prior to flow reversal. As soon as the flow basically becomes stagnant before it reverses, and then it closes the valve. We'll dive mostly into these quarter turn valve applications for today's session. These two are the butterfly and the ball valve. Differences here, you can see in the open position, the ball valve is a true full port opening, whereas the butterfly valve would have the disc within the flow. Typically you would use ball valves in most applications 2 inches and under, or in larger bore pipe if full flow is required. If you have a very high flow rate requirement where this disc on a butterfly valve would reduce flow enough that it might impact the process, then you would go to a large, a full port valve like a ball valve in this case. You can see the disc being within the flow. Typically we use these mostly for on-off applications for isolation, although they can be used in proportional or modulating applications where tight control is not really required. It would be more something to where they're just looking to kind of throttle flow to just a small amount. If you need very tight control, there are other control valves that we can discuss later that really give you really much more control than this particular type of design. You can see the typical design. You've got a stem that comes through what's called a packing area here in both of these valves. The packing here is what prevents media from coming up through this and leaking out to the atmosphere. And the stem is what actually drives, in this case, the ball or the disc to either the open or closed positions. So that's how it's actually operated. In this case, you've got a lever operator here that can be open and closed by hand. Within butterfly valves, there's a couple different types. We've got what we call a resilient seated valve, or rubber or Teflon seated. These are usually general purpose applications. Being that they are rubber or Teflon lined, there are greater restrictions on temperature and pressure for these type of valves. A typical resilient seated valve, you would use in applications up to about 175 PSI. Not sure what that converts to in bar. You guys probably use more bar units than PSI. But like I said, we do have some that are rated up to about 250 PSI, but they would still be temperature limited with EPDM or some of those. You're usually looking at about 225 to 250 degrees Fahrenheit. So if we've got applications with higher temperatures, we could go to what's called a double offset or high performance butterfly valve. That's this type of design. Those are typically as a standard offered with a Teflon kind of an O-ring seat. In this case, that design is actually made so that you can see the disc is actually in front of the stem, as opposed to in this case, it's called a concentric for resiliency of the valve. So that stem goes directly through the middle of the valve or middle of the disc. And in this case, it's the seal is created by the disc making direct contact with the seat in what we call an interference fit. In this case, this is more of a position seated valve to where the disc is actually driven into position and seals up against the seal, which is retained within this body. You can see this retainer ring there. It's actually retained within that valve body. Again, touching on ball valves, we've got a number of different designs here between these three-piece valves, which can be either threaded socket weld ends or butt weld, or we can get into flange end connections where those are actually bolted to the flange into the pipe wall. So those are kind of the different end connections that you've got. And we've got a number of different body designs. This three-piece design is made to where it could be easily the center section be pulled out of line and repaired and then reinserted without taking the end connections out. So if you've got this welded in line, you can actually still repair the valve in line and then maybe get it back into service. This goes a little bit more into kind of the size range and pressures and temperatures. As I mentioned, resiliency of the valves. In this case, go from about 1.5 inches to 72 inches, which is pretty large. There aren't many resiliency of the valves over 36, but there are some. Usually in those cases, they go to some different type designs. There are some seats that can handle up to about 300 degrees Fahrenheit. One of those being Viton. But max pressure rating for this particular valve here, this with the blue body, that's a molded in seat that's actually capable of 250 psi, but is still somewhat temperature limited. Then we go to the double offset design where we can get the temperatures up to 600 degrees in in what we call a metal seated valve instead of the Teflon O-ring seat. We actually have a metal seat ring there, and in an ANSI class 600 that can do up to 1480 psi. So you can see a significant jump in the design of that valve to handle those higher pressures and increased temperatures. This valve too, because there's a resiliency of the valve, the media is actually the body is actually isolated from the media by that resilient or soft seat. So when you've got a rubber seat in this fashion, it can protect it from a lot of corrosive medias. Whereas the double offset or high performance valve, the body and the disc itself are actually a wetted part. So in some cases, we go to, like in this one case, would be an aluminum bronze body and disc for seawater applications where the high chloride content of salt water would cause corrosion. So we can go to certain higher alloy metals that would help stand up to those type of more corrosive applications. This cavitation control is a unique modification of the double offset design. It's basically the same valve, but they actually do a contoured disc. And you can see here this external seat retainer actually has a diffuser plate that's kind of built into the outlet of the valve. And what that does is that allows for increased flow control. It'll actually reduce flow at lower or at areas from say 0 to 20 degrees open. It'll actually increase the amount of control that the customer can get, but still in a pretty compact design as opposed to globe type valves, which if we were looking at a 12-inch valve here, it would be a very large valve for a globe control valve that we mentioned on the first slide for throttling applications. This would allow you to do the same thing and get similar control, but in a much more compact and cost-effective package. Going from a double offset to a triple offset is a unique, or it's just kind of a design advance to where, as I mentioned, the disc here is behind or is in front of the stem. So that's what we call a single offset or a double offset. It's actually not only behind it, it's actually slightly off center. And that double offset design, I liken to an airplane door, to where when those are opened, you actually pull that door out from the plane and then it rotates to the side. So it's a very similar type geometry there. So it reduces seat rubbing because in this case, the disc is always in touch with the seat. Here, it's only in touch with the seating area really at the last 3 or 4 degrees. Triple offset takes it one more step in that the seat itself, the sealing element is actually on the disc here, and there's a seat itself that's typically an integral part of the body, and it's machined. There's a machining angle that reduces that contact point even further to where It's what we call a torque seated valve. So it will actually touch the seat only as it's sealing immediately. And in these set valves, it's a full metal to metal seal. So it can handle even higher temperatures in this case. So up to 1100 degrees. And it's a torque seated valve. It can create really reliable sealing in critical applications. In similar pressure ratings to high performance, but increased temperature ratings because it is a truly usually an in canal seating within the valve body, and then the disc seal itself can be made of several different combinations depending on pressures and temperatures of the application. Going on to ball valves themselves, these, like as I mentioned, these are more typically are full port valves. We've got them in flanged ends where they would bolt flange to flange in 150 and 300 class. There are many out there that go up to 600, 900, 1,500 pound class for very high pressure applications. And we can do these in what we call V-port ball valves instead of a full port. So if we wanted to use this as a control valve, these would give us, I don't know why that keeps switching on me. These would actually give us tighter control for modulating applications when we can get into very finite control of the media. Then we get into flanged multi-port valves. So if you've got either what we call a diverting or a mixing application where you've got two inlets and an outlet, the multi-port valves themselves, we can set those up with to either be diverting valves or for mixing applications to take two different flow streams and either alternate or mix those. We use those a lot in the kind of hot water applications where it might be mixing steam and cold water to create hot water. And there's control systems that can help modulate that to gain desired output temperatures. Segmented MV1F series, that's also another control valve. It's a single seat valve where it's only got, instead of a fully round ball, it's only got a half ball, and that's used for typically more difficult medias where there's a lot of suspended solids that might collect within the ball itself of a traditional ball valve. So those are used in specific applications where it might be a little more challenging for a typical ball valve. The last two to the right are really small bore threaded end, or well, the M22 series, that's a threaded only valve, and then the M32, that's what we call a three-piece valve that allows you to do, as I mentioned before, kind of replace seats and seals. It comes in a variety of end connections, pretty versatile, a lot of applications. Just a little bit more into the design of the valve. As I mentioned, there's multiple end connections between flanged, threaded, socket weld, and butt weld connections. That's typically end user driven, whether they would, sometimes contractors like to use threaded valves, or sometimes they prefer socket weld. Sometimes it's customer driven. Flanged end valves are obviously typically easier to replace the entire valve because they can be unbolted from the line. I shared a little bit of this just to really show kind of some of the different the overall build of a particular valve. This seat here, item 15, that's actually the sealing element that seals against the ball in a ball valve. And then you've got body seals in here that help just that allow to seal between the center section and the end connections of the three-piece valve. And then we can do a variety of bill of materials here. In this particular case, we've got stainless steel body and a carbon steel body. Other than that, the materials would be very similar in these two. But if you've got certain medias that are more corrosive, you would certainly go to a stainless steel valve, or it's driven by the piping material. If it's built with carbon steel piping, then typically they'll go with a carbon steel valve. This down here shows a little bit more about the ease of maintenance with a three-piece design like this, to where you don't have to remove the end connections from the valve. So typically a welded in valve can still be repaired. It doesn't have to be just cut out and then a new valve welded in place. This allows you to change out these seats and seals here, and then put it back in line. Now, a little bit into the actuation side of valves. So we've got anything from a very basic manual operator, in this case, a lever handle, or a gear operator. We typically see lever handles on valves 6 inches and below, and then 8 inches above that tend to go to gears. Although that is a little bit fluid depending on user preference. But that's mainly due to torque. As the valve gets larger, there's a lot more operating torque to close the valve, especially under pressure. So that's when a gear operator is beneficial to create additional, more torque than we can do by hand. This is kind of a unique application here where we've actually got what's called a limit switch on top of this lever handle. That's there just to provide a control system that's within the plant. It would give them an actual indication back whether this valve is open or closed. So there's actually a switch in there that would make contact depending on what position the valve is in. So that becomes critical in some cases where if a certain valve is open, the operators need to know that, and it sends that signal back to the control system. Other rotary actuators that we'll touch on today are pneumatic actuators, which is air operated. So any plant that's got a compressor and they'll be running pneumatically operated valves in most cases. Pneumatic actuators are typically faster operating. And then we can do electric actuators, which are just an electric motor operator. Those tend to be slower than pneumatic actuators, although there are some that are fast acting. But in general, they are slower. They would run from full open to full close, typically anywhere from a standard unit would be anywhere from about 30 seconds to 90 seconds, depending on the size of the valve and the motor. In this case, you would use a number of different accessories. In the case where this a valve might be just an open closed type service for isolation, or in this case, they're showing a couple of positioners on top of these pneumatic actuators, which would accept a 4 to 20 milliamp signal to modulate the position of that valve to again throttle flow through the valve. Some more examples of manual operators. In this case, we've got some stem extensions where maybe that was the valve is at a lower grade level, and we want to bring that operator up above grade so it's easier for operators to handle. And then over to the right here, we've got actually a chain wheel operator on that might be something that's overhead, and they would have a chain drop that would come down typically at chin level or so to be able to operate that valve from the ground. A little bit more overview on some of the operators. We've got, again, a couple different types of pneumatic actuators. We'll touch more on those later. Electric actuators on high performance valves. This is an electric motor operator with a remote mount control station. This would allow the user to either put that in local mode where they could actually control it right there. This would either be close coupled on the unit, it would actually be what we call nipple mounted on the end of the side of this actuator, or it could be mounted to the side somewhere if the motor is at a higher level. You can actually run this control station down and give them the opportunity to sorry, that's why this keeps moving. It would allow the control station to be remote mounted, but they can actually put that in either remote mode where the control system for the plant would be operating it, or they can operate it locally. A little bit more into pneumatic actuators. There are a couple different types. We've got our pneumatic rack and pinion design. That's typically for smaller actuators and small modest torque outputs, and then we get into what's called a Scotch yoke type, which is this orange one here. That's meant for much larger valves. It's got a different torque profile that creates more operating torque at the beginning and end of the stroke, whereas the pneumatic rack and pinion is a pretty constant torque output. For ball valves, rack and pinions tend to be really good because the ball is in contact with the seat the entire stroke, so the torque profile is pretty steady throughout the stroke of the valve. And then a butterfly valve, Scotch yoke can be better for those, especially when you get in the larger bores, because most of the torque is really just at the end, as it's especially in a high performance valve where it's just when it's seating, that's when most of the torque is needed to be applied to actually create that seal and get the valve into the full closed position. Again, these are air operated, so you're using compressed air. These often, with the accessories that they come with, we typically will use filter regulators to regulate not only the pressure inlet to these actuators, because some of them are pressure sensitive. They could be rated up to about 140 psi inlet, or some of the Scotch yokes might be rated down as low as about 80 or 90 psi inlet. Any more than that could cause damage to the actuator. So we do regulate those, and then we usually use a filter as well to ensure that the compressed air coming into that is clean and doesn't introduce water or debris inside the pneumatic piston, which can cause wear and damage. This is kind of just to show that the typical setup of an automated valve package. You've got your, in this case, a butterfly valve mounted on top. We've got in this case, a rack and pinion pneumatic actuator. You can see internally this has got the pneumatic pistons where you would introduce air to one side to stroke it open, air to the other side to stroke it close. And then we've got what's called a limit switch, or in this case, for feedback. And this would typically include two switches, one for open position, one for closed, and that would provide indication back to the control panel as to the open or closed position of this valve. So that's typically very critical for plants to know in certain cases whether a valve is open or not, so that they can manage the process and not have in some cases flow into areas of the plant that's that's not under operation currently. Again, a little bit more on the rack and pinion actuator. You've got two air ports. One, the right port for the to drive it to the closed position in a typical setup, and then the left port for open position. You can see here the air would enter the right hand, or would enter the port to open the valve, and then it would exhaust air from the other side during that stroke. We can also do these in what's called a spring return feature, which provides a fail safe. Could be either fail open or fail closed, and you would have the springs that you saw. I don't think they show them in this one, but the springs that would be within the housing here on the end, within the end caps, that allow for a fail position. In that case, you would only use air to stroke it in the opposite direction. So if it's a fail closed, that actuator would be what we call air to open and spring fail closed. A lot of plants use that because they want to ensure that even if they lose compressed air, the valve would be in its normal position without, in that case where they've lost their compressed air. Just a little bit more about the internals and design. You can see the actual the pinion here, and then the pistons that are driving that pinion, and the springs as well that show that this would be in a spring return fail safe application, where you would introduce air to open the valve, and then the springs would take over and drive the valve closed. And this is typically controlled. The air is controlled into the actuator by a solenoid valve. We can either have that mounted to this, or it could be a panel mounted solenoid, but those are used to be able to control that airflow into and out of the actuator. You can see a better view of these spring cartridges. These are actually self-contained spring cartridges, so they're very safe to deal with. It's they're kind of preloaded here into a cartridge. Very easy to change out. You can add or remove springs. They typically take up to 6 springs per side, depending on the amount of valve port that's required to close or open the valve. A little bit more on the Scotch yoke design. You'll see how it's got the rod that would actually drive this, the air would be introduced here, it would drive the piston closed, and then it's got this yoke that the piston rod would turn, so that would actually turn this pinion here to drive the valve. And like the typical symmetric yoke, you can see the torque profile, like I mentioned here, versus a rack and pinion, where a rack and pinion is very flat. The torque is pretty consistent across there. This provides more torque at the open and closing. So in some applications, that's really desirable, where all the torque is at either the open at the 0 degree or 90 degree point. So it can allow you to use a kind of a smaller actuator, because it's got increased torque output at the ends and reduced throughout the stroke. Canted yoke is just a slightly different geometry, and it increases the closed end or 0 degree torque. Again, that's typically used in a butterfly valve type, where all the sealing is really just, or all the torque is really just at the sealing moment where the disc is riding into the seats. Mechanical overrides can be used to allow you to open or close the valve regardless of the actuator position. This is often used just in case if they do lose plant air and they want to be able to open or close a valve, they can do that. Or if they just want to manually override something, they can actually engage this gear here. It'll actually uncouple the gearing inside from the actuator itself and allow them to use this hand wheel to operate that manually. And in this case, this is a similar type thing with a hydraulic hand pump or hand override. So that can actually allow you to drive that and overcome the air that's being provided to the actuator itself. Kind of a safety feature in a lot of cases, depending on plant requirements and needs. As I mentioned before, the air is typically controlled into these actuators with a solenoid valve. They could be a panel mounted somewhere else, or in this case, this is what I call it a Namor mount, or a direct mount to the actuator. The plant would apply air to the air port, which is typically underneath the side here, and then this coil can be energized to drive the spool valve inside there to direct air either into the open or closed side. In this case, we've pre-wired this to this limit switch, so the electrical coming to the solenoid and the feedback from the switch can all be wired into the solenoid or into the limit switch itself here. This makes things easier as opposed to running wires to the solenoid and to the limit switch. Everything can be landed inside the terminal strips, which you'll see here inside the limit switch itself. And this switch box here, again, is just for open and closed indication. You've got a visual beacon here that would show visually what, the valve, whether it's open or closed. And there are contact switches in here that then again provide that mechanical feedback switch and indication back to the control system as to the valve position itself. This is a breakdown here of the solenoid valve itself. That's the spool valve inside that slides back and forth based on the coil being energized or not. And that's again what directs the air into the proper side of the actuator to stroke it. Again, we talked about isolation applications where you typically would use a limit switch for just open and closed indication. In this case, this would be a positioner that would accept a 4 to 20 milliamp control signal, and that could vary. You could have 4 milliamps as open and 20 milliamps as closed, or it could be an inverse signal where 4 milliamps is open and 20 is closed. But that allows you to go anywhere from full open to full closed. You could give it a 12 milliamp signal, which would be 50% open. So this is used to be able to throttle a valve. If you have a process that requires varying loads of media, you would have some typically a downstream like flow meter that would be measuring flow, or some process instrumentation that would say you need a certain number of GPM of hot water to get the batch or whatever process they're doing to the proper temperature. These modulating positioners would allow you to modulate that flow and really control flow through the valve to a very precise level. These can be used to really control the process conditions very tightly. Get more examples of electropneumatic positioners. Again, these are accepting the 4 to 20 milliamp signal. In this case, proportional control, but then you also get you can have feedback from this where it'll actually send a 4 to 20 milliamp signal back to the system to kind of as verification. So it's a good safety feature to know if you're giving it a 12 milliamp signal and you're only getting 8 back, then there might be a problem that the valve is not able to stroke fully. So it's almost kind of like a double check to where if you're giving it a control signal, you should be getting a matching control signal back to the system. So that's a good way to monitor your system to know that the valve's performing and is going to the desired set point that you're giving it. Now onto electric actuators. Obviously, these are motor operators. We're seeing the industry shift more and more away from pneumatics to electrics. They tend to be a lot more cost efficient. Pneumatic actuators require compressed air all of the time, whereas electric actuators, they don't consume any power unless they're actually being operated. So it can stay in a steady state and not consume any power until the next time that it's energized to be able to stroke the valve to another position. See, these are powered by electric motor instead of pressurized air. You've got a gear train inside. You've got your limit switch sets, and you've typically got some additional auxiliary switches, which can be used to control different things within a plant. You can have an auxiliary switch trip to tell the system to turn a pump off or on. Typically, a little bit before the valve is closed, you would want an auxiliary switch to trip a pump to turn the pump off, so that the valve is not closing against a pump that's running, which can create problems. You can deadhead the pump and cause damage to the system. So typically they'll use auxiliary switches and maybe set that 5 or 10 degrees from fully closed. So as the valve is stroking, going from open to closed, it would kill the pump prior to that valve fully closing. Again, just kind of the setup of a motor operated valve. You've got a drive sleeve down here that engages the stem, that turns the in this case the disc open or closed. You've got engagement of the disc, in this case a resiliency valve, where it engages the stem engages the disc that turns it, and then the disc itself is engaged with the seat to create that seal and prevent flow by in the closed position. A little bit more on motor operators. We've got conduit entries here that would allow the plant to bring in bring in all their electrical wiring. There's terminal strips inside where they connect. It also allows for feedback in the cases where feedback's required. This is just basic power wiring. The current enters open, line drives the motor until it's open, and then it would do the opposite when that motor is energized again. Again, just kind of a setup on an electric motor. This is most of these motors will have a hand wheel override too. Again, in the case where either you lose power or you need to be able to drive that motor to a specific position. Most motors are what we call fail last position. There are some that that actually we'll get into in later slides that will discuss the differences in some that are what we call a fail safe order that would provide a fail safe on loss of power. So again, there's the manual override, and then a local control unit where you can put this in local or remote. It gives local indication of the position whether it's fully open or closed. It's also got a power LED that'll just show that the unit
Kevin, are you speaking?
I'm sorry?
Were you speaking?
Yes.
We stopped hearing you,
Oh, okay, I'm sorry. Yeah, I'm not
and
sure what
we're no
happened.
longer seeing the presentation.
I can just share it again here.
Okay, cool.
Okay, now we're back on. I'm not sure if this is having a mind of its own here today. Let's see here. I think this is okay. Well, okay, yeah. So getting into more of the mechanical electronic fail safes, we've got a spring return motor upper fail safe. You can kind of envision it's kind of a motor operator on top of a rack and pinion design that provides a mechanical fail safe. These are used typically in kind of critical applications where a plant loses power and the valve is in say an open or a closed position. It can cause some fairly catastrophic damage or real critical process problems. They can use these mechanical fail safes. These tend to be somewhat limited in torque output, so depending on the size of the valve, it may or may not be an option. Some newer technology, the SuperCap series, or SuperCap failsafe, is actually a capacitor bank within the housing itself that is charged up when the unit's powered and stays charged, and it provides enough power that upon power loss to the motor itself, it would have enough power to drive it to a preset position. So this MA series here that's shown, it's kind of an intelligent actuator, and you can actually program it to go to a preset position upon loss of incoming supply power, and it would use that energy from the capacitor bank to drive that motor to that desired position. If you've got either larger units or a number of units that you wanted to control, this EFS battery backup system is a kind of a standalone battery bank that would allow you to control one up to about 6 or 8 units, and you could go up to the much larger, higher torque units without requiring a mechanical fail-safe like this or a capacitor bank. This would actually allow you to provide fail-safe to a number of units and set up the higher torque outputs. Some of the advantages and disadvantages, as I mentioned, the electrics are pretty efficient. They only use power when they're actually in operation, not when they're in just standby mode. They're typically very easy to set up. You're not worried about running a lot of compressed air lines, and you don't have a number of other accessories like solenoids that can get fouled up from poor air quality. They're much easier to put in remote areas. You don't have to run a compressed air line a mile out to a unit that's maybe in a very remote area. They can run electric. Sometimes they can even use solar power battery banks to power units they're pretty much autonomous out in the middle of nowhere. Also, these give really precise precision control, and because they operate slow, a water hammer is not nearly as big of a problem. If a valve closes too quickly when there's fairly high flow, it can cause what's called water hammer, where it would close so quickly that the flow would hammer against the valve itself, and you can actually see it shake in a plant when they've got water hammer issues. It can actually tear stainless steel piping apart, tear flanges off the piping. So if it's depending on the size and the volume of water, it can really cause some serious problems. So motors are slower, and it really reduces or almost eliminates issues with water hammer. Disadvantages: if you needed a fast cycle time, maybe in air applications, pneumatic operators are much faster. Pneumatic actuators are much more cost effective for fail-safe applications. These spring return electrics can get fairly pricey. And then, of course, there are, like I mentioned, a kind of limited torque range for electrics. This is again just an overview. We've got the Intelligent series, which comes either in a standard or that fail-safe with the supercapacitors. We've got kind of our standard heavy duty unit for ordinary locations, and then hazardous duty, which would be in areas where there's explosive dust or gases that could be in a confined area. Sometimes those require what's called like class 1 div 2 area classification ratings, where these housings are rated and sealed to not allow any electrical output from the unit, like sparks or fire of any sort, that could cause an ignition in a hazardous area. And then again, the spring returns available both in ordinary and hazardous duty as well. This just goes more kind of the same thing, but just talks about torque range. These torques are rated in inch pounds. You can see the smaller intelligent units rated only about 1,700 inch pounds, which is fairly small. And we can get up into about 40,000 inch pounds in some of these heavy duty units. And then you can see the spring return, like I mentioned, these are somewhat limited because of the mechanical spring return up to about 3,500 inch pounds. I would say that's probably about an 8-inch butterfly valve. Whereas, we can do a 40,000, that can do like probably a 24-inch butterfly valve. Selection criteria, things you have to consider when you're selecting for motors. Temperature ratings, they have a pretty standard temperature range, but if you get into certain areas, what we call, they might need like kind of an Arctic package for very low temperature items. Sometimes we see some really high temperature ones where they're in maybe damper tunnels where the temperature can get up to a couple hundred degrees, and sometimes you'll need to do some high temperature seals for the housings and stuff, so that those rubber seals don't degrade from temperatures. You need to consider the location, whether it's a standard or hazardous area location. And like we mentioned, do you need fail safe? Do you need, if you lose power, would you need it to automatically close or open? There's some options there, and then it's into the control functions. Whether do you need it to be just an open close for isolation? Do you need it to modulate? The rest of these, like Modbus and some of these other ones, we'll talk about just briefly. I'm going to touch on some of the control systems that are out there. Again, it's always important to know what voltage is available, whether it's 120 volt single phase or you get into 3-phase power. Typically, I believe down in Jamaica, I think there's a lot of in a lot of the plants, there's a lot of 580 volt 3-phase units, which is very high voltage. So it's important to know what kind of voltages that are available there to drive the motor. Do you need local controls, like a local control station, or a hand wheel override? Environments, NEMA 4 is basically just weatherproof, or IP67 NEMA 4, that's weatherproof. IP68 NEMA 6 NEMA 7 or NEMA 6P, that's actually submersible. So you've got an application where it gets a lot of maybe overspray and water or other media. You might need to upgrade the housing just to ensure that it's what we call almost submersible, and wouldn't allow water protrusion into the unit. This touches a little bit on network communications. So there are, when you get into larger plants, like say some of the bauxite mines down there, you may have a control system, and what they can do is they can use some of these process control networks to be able to communicate with a number of these different units throughout the plant, so that they can actually, from a central control station, they can get they can both control the valve and they can get feedback. They can get kind of data logging, so they know if there's problems with the valve, that they know that the valve's not performing, and they can get a lot of information and process control back through these systems. So basically, there's different systems. One's called OSI, another called DeviceNet, Profibus, and then Fieldbus, Fieldbus Foundation. And we'll just kind of touch on those a little bit. There's a lot that can go into these kind of control systems, but just being aware that there's a lot of different control systems out there, and it depends what a plant is typically built with as to what they might be using within each plant. So this goes a little deeper into OSSI and some of those is a fairly simple control system. It basically gives you very basic control. OSSI is good because it requires a lot less wiring than some others. It's a very simple system. Doesn't provide as much complexity or as much really feedback. There's really no data logging capabilities with it. Then you can get into things like DeviceNet that can work on a lot of several different systems. It can provide a lot of feedback. It can work with multiple units, Profibus, HART, and other things that just provide communication to those units. And then really the most advanced system would be your field bus foundation and Profibus that would allow you to Profibus PA, which allows you to do a lot of different things and do a lot of data logging features and you can actually do analysis on valves and they can actually predict failures in some cases. If it sees valve torque increasing, then it can warn you that there could be a problem with the valve because the valve torque has gone up 20 or 30%. And so that can allow you to address issues before it becomes a problem. A little deeper dive, just some of the different features as far as what's required. Some of them are 2-wire control, some of them are 4 wires, that just meaning that how much control wiring is required for some of these different systems, how much power each one consumes. There's some limitations sometimes on maximum run distance from a controller, and the number of sometimes the number of devices that it can monitor at one time. So, like I said, some of these have diagnostic. The Field Bus Foundation is the best with being able to do some predictive analysis on your valve packages to know whether there's failure issues that are possible. That's really the most advanced. OSSI itself, pretty simple system. It can work on some different network types. Like I said, pretty much lower installation costs than some others. Not too much more than just typical, discrete systems that are very basic, but it does give you some more simplicity in use. DeviceNet, just a little overview of that. It gives you some diagnostic features, give you some alarms that can kind of give you some warnings and give you a little bit more insight into the system. And then also like it gives a little bit more visual indication for open and closed LEDs, and fairly simple wiring still when it comes to these. Profibus, much more advanced. It can transmit a lot of information back and forth, and this is typically used for larger systems where you've got a number of units on it. It's pretty fast transmission speed, so they can be very responsive to changing process conditions. HART's a pretty simple communication protocol, and it integrates well with a lot of different control systems. Delta V is a very common kind of open source control system, and it works very easily and well with that. HART units actually have a wireless communication device that you can use, so you can actually be locally at the unit, and you can control it through a little handheld device, kind of like your like a garage door opener almost. It's a very small little, almost key fob type unit where you can open and close a unit with a very simple device. This is just a real basic layout of how a plant is set up. You've typically got your asset management software that's set up on a plant Ethernet system, and then that runs through a bunch of operator stations that the operators can control units from there. And it goes all the way down to the valve level itself, and they'll run communication protocols through there. So again, you can control a number of devices in a number of different ways, and do a lot of data logging, and monitor systems very tightly from this whole network. I'll feel free to share this. There was just a bunch of technical information that can be available through this. In case this is one of our main manufacturers, Maxar Technologies, who I focus most of the product that was shown is their product, and they've got a lot of good technical information CAD files if you're doing drawings that can be dropped right in to include into the drawing. So you've got the complete schematic of a particular system. A lot of technical brochures, and then some unique FAQs and kind of case studies where certain solutions that we've developed over time can be shown to help you identify good solutions for your process. That's really the main part of it. I have a couple more slides if anybody wanted to see them, but that was pretty much most of what I was planning going over for today. And if there's any questions at this point. You see one question.
Yeah, you can go ahead.
Yeah, I was just gonna ask someone a question about the best applications for ball valves and butterfly valves. They can be used somewhat interchangeably. Like I said, a lot of times it could be based on flow rate if it's required. If it's a very small pipe size, say 2-inch and under, a 2-inch butterfly valve with the disc in there would restrict flow, and sometimes that's not necessarily desirable. So a lot of it's designed around maximum flow rates. But like I said, when you get over 2 or 3 inches, a butterfly valve becomes a lot more cost effective. So if it's not a real issue with a little bit of a restriction in flow, then the butterfly valve becomes a much more economical. I mean, you can imagine a 12 or 16-inch butterfly valve has got a very thin profile, whereas the same thing in a ball valve would be much larger. Well, you did a flange valve like this, a 16-inch valve, that would weigh about as much as a small SUV. I mean, they're very large. I mean, I've seen 24-inch ball valves that were certainly as much as a full-size truck weight-wise. So some of those can be, so just a lot of it's required on that, or it could be a temperature requirement because we typically are using Teflon seats that are good about 450. Whereas a resilient seated valve may be temperature limited unless you go to a Teflon seat like these, or some high temp seats that are good to 300. So there's a few variables that do go into there, but I guess, like I said, line size and bore size and flow rates are kind of the main factors for that.
Okay. On this same slide, what is the meaning of class?
It would be the pressure class. So down here, pressure classes are based on the flanges that they made up to. So that's basically a temperature limit, or I'm sorry, a pressure limitation. So an ANSI 150-pound class is good to a certain pressure rating, and then you would need to go into what's it called, an ANSI class 300. It's also in metric, it would be what's called pressure nominal, PN. So a PN 10 would have a certain pressure rating, and if the system pressure is going to exceed that, you go to a PN 16 or PN 20. In this case, like I said, ANSI 150, 300, or 600. So a lot of that has to do mainly with pressure. So in this case, like a double offset, a 1480 psi would be at ANSI class 600, not a 3 or 150. So if I've got an application that's let's say 300 psi steam, 150-pound class cannot handle that. So I have to go into a 300-pound class. But don't let these numbers dictate or tell you that because an ANSI 300-pound class, it's not limited at 300 psi. It's really more like 700. So it's a little bit of a misnomer as far as the actual pressure rating, but it refers to an ANSI class, not necessarily a pressure class. So like a 600-pound ANSI class is good to, like I said, in this case, 1480 psi.
Okay, thanks for that. We have one more question from one of our car internals. What is the difference in using a bolted valve versus a wafer valve?
Well, in this case, a wafer, like this one here, sits between flanges, and the bolting is run from one flange to another. The other type would be, this is a lugged style. So in this case, the bolts are run in from one flange into the one side of the valve and the other flange into the other side of the valve. The advantage of a lugged valve is if you ever needed to take off the downstream flange, that valve in the closed position, because it's still bolted up on the one side, could still hold pressure. So you could actually, with a lug valve, you could have that valve closed, take off the downstream flange and do work. A wafer valve, because they're bolted from flange to flange, wouldn't have that possibility. It would just basically fall to the ground. So those are lugged are probably much more common. You see a lot more wafer valves where they're doing a kind of a large scale installation, and there's a bunch of them that you're going to have some lug valves in there because they need to have opportunities to be able to do those. They're going to be able to isolate with one flange off. But for economy's sake and saving money, they might have a bunch of wafer valves in other locations throughout there where it's not as critical.
Okay, so there's a follow-up question. Which one would cost more?
The lug costs more because there's a little bit more material to it. You got your lugs, especially when you get a high performance valve, you got the lug, all the different lugs that are cast into it. So there's more material cost there. So I would say the cost difference, depending, it varies a little bit on size. Probably the difference increases the larger the valve gets. It's pretty small on a 2 and 3 inch valve. But I would say if you get into a 12-inch valve, it's probably about 12 to 15% more for a lug valve than it would be for a wafer. See, these two are in the high performance, that's a wafer design there, and then these are lug.
Okay. And another follow-up. Which valve is best for a high abrasive 250 Fahrenheit, 250 PSI application?
For abrasives, I would tend to go, let's see, right slide to figure out this. I would tend to go with a metal seated valve and typically this segmented valve that's it doesn't have a cavity in there, so it's designed to kind of cut through and handle slurries or different medias. There's also another valve type. It's called a pinch valve. That's basically got a rubber sleeve that runs through it with a pinching mechanism that would close down on the valve. Which we actually use that in a lot of the slurry applications. I know, for instance, Jamaica has got a number of those, as does Winalco there in Jamaica that use a lot of pinch valves. So there's some different types out there that we really didn't touch on, but in this case, I would not use a butterfly valve typically in something that's got a lot of abrasive meeting in it, or something that's viscous. I would either go to a ball valve of this sort or a segmented ball valve would be better.
Okay, thank you so much. Okay, we keep going. Are any of your control valves designed to be able to purge the process material away from the valve packing area?
Well, typically they're going to be sealed enough that you should not have much media that would actually drive up in there. You've got typically a thrust washer and a packing seal here that would prevent media buildup. If you're starting to get media up into the stem area, then that valve needs to be rebuilt to prevent that. And like here, they've typically all got an upper and lower set of packing to help at least prevent leakage to atmosphere. There are some cases where we can do what's called a fugitive emission bonnet on top of this valve, or a sensing port here that would actually sense if there's pressure or media buildup within that intermediate area, and that would give you a warning that you've got a lower stem packing failure. So yeah, this is important. There was all these designs would have seals that would be up in this stem area to help prevent media from going through.
Okay, thank you so much. Karine, does that answer your question? And it's a series of questions.
Here's all the different thrust washers and packing will come down through the stem and the O-ring there that helps seal it off.
Okay. All right, thanks for that. So with that, Kevin, we thank you for your time and your patience with us this morning/afternoon. We're just going to ask you to go back to the first animated slide quickly.
There.
Okay. Right.
Touch mostly on water turn valves today.
All right, cool.
I do
So
have a
if
couple
there
of
are no
slides showing some of the globe type valves if anyone is interested in those.
Okay, so I think we can probably facilitate this discussion offline after. And yeah, just you can share your contact information in the chat if possible.
Sure.
Yeah, man, to everyone. And I'll at this point hand over to Jan to close us out.
Thank you, Javed. And thank you, Kevin, for that insightful presentation. So our giveaway winners for question 1, we have Giovanni Ferguson. For question 2, Richard Artwell. And for question 3, Gary Thompson. We'll be in touch so that you can collect your prizes. And as we wrap up today's JIE Development Forum, I want to extend a heartfelt thank you to our esteemed speakers, Dr. Denton, Dr. Allina, and Kevin Perrigo for sharing their invaluable insights and expertise. Your presentations have sparked important discussions and provided great takeaways for all of us. A big thank you as well to NCB Capital Market for their generous sponsorship of our giveaways and to everyone who participated. Most importantly, thank you to our audience for your engagement, thoughtful questions, and active participation. We hope you found today's session insightful. Stay connected with the Jamaica Institution of Engineers by becoming a member. Follow us on social media for updates on future events and initiatives. Your certificates will be emailed to you. Until next time, keep innovating, keep learning, and have a great rest of the day. Thank you so much.
Thank you very much.
Thank you. Thank you.